In this video, we'll explore the concept of polarity, electron counting, and how to apply VSEPR theory, as well as vibrating bonds.
First, we'll start off with what is polarity. Polar covalent bonds occur when two atoms share electrons unevenly due to differences in electronegativity. In the fluorine-hydrogen bond, fluorine induces a dipole moment within the compound due to its higher electronegativity than hydrogen. This results in an uneven distribution of electrons between the two atoms. And you can see this due to the partial negative charge and the positive partial charge.
Key terms that we discussed in lecture. So first, bond dipole is the separation of charge based upon different electronegativities of atoms in covalent bonds. Overall, polarity of molecule is determined by summing the polarities of all individual bonds and includes strengths of bonds and orientations. Lastly, permanent dipole is the permanent separation of charge due to unequal distribution of bonding and or lone pairs of electrons.
Does this molecule have to be polar? Methylene chloride. So each chlorine and carbon bond in the molecule is more electronegative. So chlorine is more electronegative carbon. And because we have two of them on the molecule and two hydrogens also bonding to the carbon, and chlorine is very electronegative, it will create a polarity. And because hydrogen is very low in electronegativity, there won't be polar bonds or dipole moments. This means that it can't be canceled out. So either way we move the molecule, the two chlorines will still be on one side while the hydrogens will be on another side. And because there's an asymmetric distribution of charge, making this molecule polar.
Now let's briefly go over the rules of electron counting. In VSEPR, you count pairs of electrons and not all the electrons. In VSEPR, you also count double and triple bonds as only one pair. For formal charge, you count lone pairs as 2 electrons and bonding pairs as 1 electron. For the duet octet rule, you count bonding and lone pairs as 2 electrons.
When doing this counting, we go by the steric number when counting lone pairs. So we do the number of atoms bonded to the central atom, and the number of plus the number of lone pairs on the central atom. So as in the two examples it presented in class, ammonia and water, we would count these two electrons as one pair. And then we would count each bond as one electron group. So it would be 1, 2, 3, 4. And even in water, these two pairs of lone pairs would be counted as 2, not 4, because it would be 1, 2, and then the two bonds, which would also be 4. So both of these would be tetrahedral arrangement. However, because of lone pairs, they do change in the molecular geometry, even if their arrangement is the same. So both ammonia and water have the same arrangement of tetrahedral. Ammonia, as we can see, has one lone pair. So it will be a trigonal pyramidal molecular geometry because of its lone pair. However, in water, it has 2 lone pairs. So it will be bent, as in presented in the example, because of the 2 lone pairs. So it changes in molecular geometry, but the arrangement is still the same.
Next, we'll talk about the size of electron pairs. So it's important to know that lone pairs are actually longer than bonding pairs. For example, even though these two tetrahedrals here below, the molecule on the right has a slightly smaller angle because the lone pair makes them bend down more. And lastly, vibrating bonds. Infrared radiation has a frequency resonating with the bonds, causing them to vibrate. Here we have 3 different types of vibrating bonds. First, symmetric stretch, which involves both atoms moving outward from the center of the bond. Asymmetric stretch, which involves one atom moving outward while the other moves inward. And bending mode, which involves a change in the angle between the atoms.
It is also important to note that symmetrical stretch is infrared inactive, while asymmetrical and bending mode are infrared active. Thank you for watching.